All right, welcome everyone. This is part 3, courtesy of the physics department, which allows us to use the buildings late at night. All right, so where were we? So we now have new potential here. Let's take a look at this state and see what it looks like. Yeah, now we have some density. Okay. The plot still has some issues. Let me see if this works. What if we go like this? Okay, good. So this was my previous, like my canned version of plotting for this. What's on the left is the density, and what's on the right is the phase. So we haven't put any phase winding in this, but now we can try and do that. So let's do winding equals 1. Okay, so now we see that the phase winds around. Okay. All right, so we there have an initial state. Let's do the minimization again. Okay, so we can leave the s dot plot there. Get rid of these guys. Okay, then from gpe.minimize, import minimize state, m equals minimize state, s m.minimize, s1 equals that, s1.plot. That takes not too bad. We see that it's sort of smoothed out a little bit. Okay, all right. Now we want to put the phonon back in. Do we have a phonon? Oh, we probably do have a phonon. It's a little hard to see, right? That's true. Or we could, or the amplitude, right? So let's up the phonon number. Let's at least go to 2 pi, so that's like 6, right? Okay, and let's do then phonon amplitude. That should be large, right? Okay, good. Maybe a little too large. Still a little large. Where's big N? Where are you? Whereabouts? Okay, let's go. Let me just take a look at your thing. So you're in a 2D section here. Okay. Yes. Global and oh, so in your initialized function, here's where the error is. Yes. Right, and you don't have an n anywhere. Yeah, it's like you need to pass an n as an argument. Yes. For something. Okay. Let's try phonon amplitude of 0.1. Okay, so there we see something a little bit more. What? We could see 0.5, is what you're saying? Okay, we can try that. All right, so now shall we see what happens when we evolve this? Are you guys excited? We'll see what happens in a second. Let me do one other thing that usually I do differently. I don't know. I think this works, but I'm not sure. Some of my plotting functions do this, so we'll see if that works. It might not. Yeah, so that doesn't work. So what I do is I sometimes pass in my in the SOC plotters, you can pass in a figure, and then it will oh that's the problem. So it probably does work, but anyway, we'll do this. All right. There we go. The what? Oh, thanks. What? Oops, sorry. I hope I didn't muck up something you were doing. I accidentally logged into your plot. Did I delete anything by mistake? Same issue.
Yeah, that's what
R thickness?
R.
Where's that?
Oh, that is like get VXT first line. What's the property you made?
Oh yeah, you have to define this property one.
I have the same problem. And you have that property. I covered self data.
Did you define it like that?
Where do you use it?
In get v external.
Oh yeah, self.r.
I'm talking about this line here.
You want to open those brackets on.
Not if it's a property.
Oh right. Oh, just self.r.
If it's a property, yes.
You're going to call it. Why it's not?
All right. Well, then you have to define R.
I think you have the subtraction sign there where you want to be.
Oh, yeah, R, that's fine. What's R? Oh, x comma y minus?
Okay, make it so it's what you say.
Oh,
No, it's a state has no actions.
okay. What are we doing on here? Your R theta is not defined? Global variable R is not defined. Oh, we didn't compute it. It's called R2. You have to take the square root of that. Right? See, R is the square root of x squared plus y squared. You have R2. All right. Let's see what happens. It is.
And we have both flow and balloons. Yeah. Wait, yeah, because the flow is you can see but the balloons they turned off basically as soon as you just
No, they're there.
so yeah, they're potentially.
Yes.
What should I do, Jonathan?
So the phone move around to the right?
Yes, I mean I can tell that, but that doesn't help us much.
I don't know. What do you want to tell her?
I mean, tangent.
Oh, we're basically done, right? I mean, this is it. Now we have to just explore some different.
Parameter regime and like
Yeah. Yeah.
And understand this phase diagram. And
so let's look at this plotting function here. If we have 2D,
if I ask her to 15 minutes,
that should be fine. Yeah. So here's my plotting function that does this sort of thing. If dimension is 2, we do this. We get the densities, we create a subplot, we do a contour plot of the density, and then we do this angle plot. The contour plot of the density, let's do this. Okay. Okay, so what I've done here is I have modified the plot function. Maybe what I'll do is I'll actually, instead of modifying this code, which I don't really want to do yet because I don't want to change that project, I'm just going to copy this code. And we're going to put this in our example ring.
Are we going to be able to see this? Are we in on this project?
No.
Oh. Did you do it?
You're supposed to do it. I can make it public.
Because we both. Oh, you mean this specific notebook? Yeah.
Yeah, we can do something about that. If you like.
Just save the Python file and send it to it.
Yeah. Okay, so I'm going to do this here. We're going to just do the self dim equals 2. We're not going to do logs. I'm putting this in so I can customize it right here. And we don't want the 3. I get the energy, fine, 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 fine. Okay. But here's a custom plot function. And what I'm going to do is I'm going to say v, sure, I'll put this in here. I'm going to allow some keywords to be passed to my contour function. I sometimes do that, yes. Thank you. There we have keywords. So now in the plotting interval, let's just make sure this works. Let's restart the kernel. So that's the 1D stuff. Okay, now we do the 2D. Used by contour aspect. Why do I have aspect? Not sure, but anyway, okay, so now we go down here, we'll minimize the state. Now in our plot, we can go, now I have to check this and just see how this works. I am contour F. Let's see what the keyword arguments are. I think we can do Vmin and Vmax. Yes. What did we say the minimum densities were? So it's like between, say, 10 and 16? Was it 13 and 16? Okay. So this should now, there. So I've basically set the color lim, right, to be between very limited regions. Right, okay, so this isn't, so this is not very good here, but that's because we've done very small ring, etc. Now with a small ring, so let's go crazy. Let's make a big box. So let's make L, let's be bold, let's make L 60. Okay. Now our, I don't know what that's going to look like. Okay, so we have a very small ring there. Oh yeah, because we actually specified these radii. What was it called? Ring R? Okay, so let's make this like 6.
And ring thickness.
Let's make it better. Let's make it 10.
And just to clarify, ring R is the distance from the center to the center of the well?
Yes. Okay, so there's 10. Let's make it even bigger. Let's make it 15. Okay. So there's a simple little ring. Okay. Let's make the phonon amplitude big for now. No, let's leave it like that. Okay, so here's our ring. I don't know what phonon wavelength we want. Maybe, I don't know, let's bump this up to 12. Double the number. Okay, something like that. Minimization is going to be slower here. Now, at this point, we probably don't have enough points. So we'll see what's happening. What will happen is that this will fail. So you have to go to smaller time steps. Then you'll get evolution, but if this is much smaller than 0.1, then it's telling you that your lattice is probably too small. Okay? So now we're here. That ring doesn't look so, oh yeah, so this is probably a lattice artifact. What? Well, there's a rectangular, or it might be a box. It's either the lattice or the square box. But the black region out here is contours. And so it's where basically the density is 0. So it's kind of crap. It's not worth thinking about, really. Okay, so now the question that we're trying to figure out is if we change the thickness. Okay? So what were we before? We were 1. So let's make it 10. That's pretty thick. 5. Oops. And this is a harmonic thing, so. Okay. So this is an example. Now we have a very thick ring. And so the superflow at the outside will be opposite. Correct. Okay. So now we can watch this and see what happens. Let's not get rid of let's not do the Vmin Vmax here. Now the problem is that our time step has to be very, very slow. So let's evolve for 500 steps instead. Yeah, there's probably some flipping. But the question is, do we see it rotating? Okay, so here's where we need to figure out what the speed of sound is. Okay, so the speed of sound is square root. So S1.g times n.max. Let's say n is equal to s.get density. Okay. G, what? Square root of G? Like that? You agree? Okay. There's the speed of sound.
You have to divide by u dot micron and multiply. You have to give like the meter per second. You have to divide by meter per second.
Oh, hang on. We don't want the speed of sound. Do we want the speed of sound? No, because these are stationary waves. These are standing waves. Right? So what we actually want is the flow speed. Okay, so the flow speed is the gradient of the phase. which, and the phase is just winding times, well, the winding is the phase, times 2 times pi, right? And the gradient of the, so that's over the whole thing, divided by 2 pi r, right? So it's winding over r. So this is V, h bar is 1.
What do you need a name there? At least 1 over n, right? H bar over n gradient of phi is
H bar over m.
this will give you an initial velocity. We will calculate with the S1.
Okay, and do we have an r yet? Okay, so we go from 0 out to 25, right? We better not go from 0. Let's go from 1. Okay, so this is r as a function of v, right? Okay, so we'll pull this off, but this is the idea. So this is the flow speed around the outside. So that's how fast this thing should be moving. Well, I mean, the picture is that this thing should just flow. Okay, and now so the point is that at this inner part of the circle, it should be going faster than the outer part. And so then at some point, those should peel apart. But what we have to do is we have to look at this and we have to say, how many milliseconds will it take to move, for one of the peaks to move a certain distance? You have to multiply by that number. Okay, and you've got to figure out then how this is going to go. Okay, so the analysis now starts. So you take the 1D simulation, you calculate the speed of the flow this way, you look at those phonon peaks moving, you make sure that those are all consistent, and now you do it here, and you look at the inside and the outside, and then you find out when these things will stay together and when they'll fall apart and try and come up with some general criterion. That's the project.
He has to do lots of scaling business.
Make sense? And we see almost, I mean, this is already pretty interesting. So I think this could be very nice. And it's not so hard to do. Is it clear, basically, how to play with this now? Okay, good. So we will end this now, and then we can pick this up later on. You've at least generated one pretty picture. Okay, bye.